Good afternoon, everybody. Great to be here again. I think it's my fourth COV conference, so I'm one of those folks that's been here all 4 years so far. My name is Tredinnick. I'm from the University of Wisconsin-Madison. I work at the Wisconsin Institute for Discovery. It's an interdisciplinary research center on the University of Wisconsin-Madison campus. It combines information technology, biological sciences, sort of a research institute that encourages collaboration and sort of new research directions. So I'm going to give a talk here about combining LiDAR data sets with VR display technology. How many people use LiDAR here out of curiosity? Cool, quite a few. So many of you have probably run into various challenges with them, and largely how this will go is I'll kind of give a little bit of history about our group and why we started doing this. Talk about some of the motivation therefore, and then get into some of our solutions and then some of what it's enabled. So other applications that have kind of diverged from a large project that kind of kicked it all off. So the Wisconsin Institute for Discovery, we're in Madison, Wisconsin, not too far on the map. I found out a little bit otherwise this morning as I drove down here, but I shouldn't complain. Other people here probably from like Australia and stuff. So yeah, as you can see, it's sort of right in the heart of the campus and a lot of interesting things happening in the building. We have a 6-sided Macdine built VR cave at our research group, with our virtual environments research group there, a power wall and various HMDs, and then a LiDAR scanner. A little bit of history. So how this all kind of kicked off, it actually started with the construction of the building. So the former director of our lab VR space is Patty Brennan. She started the Living Environments Laboratory. She was a nursing and engineering professor for 25 years on UW-Madison campus, and had an interest in applied home and the health care technology type research. So also had an interest in virtual reality. So at the beginning of the building, she was one of the recipients of one of the internal funding awards to start a lab space in the building, and started the lab where the 6-sided cave was built down the lower level of the building. That was all in about 2010, 2011. And then 2013, we hit upon a R01 AHRQ funded grant called VizHome. So this stemmed from her 20 years of prior research. And essentially this enabled us to try to study health in the home in a new way, using VR technology. And the whole idea behind the grant was to try to understand how does the interior of the home, how does home context affect someone's ability to manage diabetes in the home. We specifically chose diabetes in this case. The concept could most likely be applied to other ailments, other issues. And then just a side note is that we were sort of rebranded in 2016 to the Virtual Environments Group with a new director of the building. Yeah, so you can see the logos look kind of similar. So based on this VizHome grant, the problem became, well, we want to be able to study these home environments in VR using our cave, but how can we do so? And what the project ended up doing was actually, as a part of the project, we went out and scanned 20 homes in South Central Wisconsin, people that had self-reported diabetes, and basically used a LiDAR scanner to create very high resolution point cloud models of these actual home environments where people live. And the hope would be, could we use this technology combined with VR to study any home in existence? Started with the 20 just to start small, but I'll talk about in a little bit about how it's pretty much gotten to the point where we could do this for any physical space. So why would you want to use LiDAR, I guess, instead of trying to model someone's home? Well, it's pretty obvious. I mean, that's incredibly difficult to do. There's so many different objects in a home. In reality, there's a lot of clutter, a lot of things that you couldn't just have an artist 3D model. It would take months and months of time. And I think it's probably the reason most everyone here uses LiDAR is for applications like this. So essentially this kicked us off, and we, as a part of the grant, we purchased a Ferrofocus S120 LiDAR scanner. This was back in 2013. So some of you may also have the same scanner. It's got a 360-degree horizontal field of view on it and 300-degree vertical. It has a very high range and resolution. The trade-off for this then becomes how long do you want to wait for a single scan to operate. For those not familiar with LiDAR technology, essentially how it functions is it stands on this tripod. You turn the device on. It's all battery operated. You use the touchscreen to set up your settings and your resolution quality settings. And you kick it off, walk out of the scene, and it'll operate for a set amount of time depending on how many points you want to acquire for a single scan. So this goes from 5 million points in a single scan up to I think it was 760 million, and at that point you're getting really, really high resolution data. And the trade-off there is that you're also getting a lot more data, so you eventually run into data storage issues, and I'll get into some of those problems in a little bit. So the weight of it was 11 pounds. I can actually, this past semester, I'm proud owner of a cargo e-bike, so I actually have put it on the back of my e-bike and driven around Madison to different homes to scan. So I feel like a scanner delivery boy or something like that. So we did 20 homes back from 2014 to 2015, and we're currently we have about a year-long, smaller internally funded project where we're actually going to be aiming to scan another 30 this year with the same scanner. And this is going to be more for a home modifications, more of a design-oriented research project. And I'll touch upon that a little bit more later. So we've looked at additional scanners over the years. We've actually, Faro let us test one out at one point. And there's some benefits, there's some improvements, there's HDR, there's better camera for sure. But we honestly didn't see a whole lot of difference in the time for an individual scan. So we've kind of just hung back and relied on this guy, and it's been pretty reliable for us, which has been nice, knock on wood. So what do we need to do then upon getting this LiDAR scanner and upon obtaining this data? So this is kind of the current pipeline, and it's taken years to get to this point. We've had different versions of this over that time span. But I guess this is what I would recommend to someone. Should you be looking to figure out a way to do this as well? We iterated on different settings of the scanner, and what we found is that there's basically a setting you can operate at that's 44 million points in a scan at a quality level of 3, which the quality indicates how many samples it takes per angular increment, and then it averages those different results it gets back together. We found you can operate that, and it only takes about 7 minutes to scan. So we've actually found that ends up being kind of the biggest bang for your buck in terms of letting it run, moving it somewhere else. There's other settings that, I think the next one down is 28 million, but then there's not much of a time difference there. So this is just kind of the unwritten kind of workflow that becomes helpful with some of this stuff. So what we do after we'll go take it somewhere, scan a space. All this is very dependent on the actual space you're trying to scan. As you know, on average, we probably take us 2 to 4 hours for a normal size house, a home interior. We then take that into Faro Scene, which is a software that comes with a scanner. Educational licenses for it are very reasonably priced, like $60 a license, I think, or something like that. And the software itself has improved greatly over the years, in my opinion. It's started out a little iffy early on, but a lot of the registration tools, a lot of their filtering tools have really improved. So we'll bring the scans all into Scene. We go through a sort of a step-by-step process there for registering. There's a couple extra steps you need to take for cleaning up, like mirrors when you're scanning interior environments, which I'll get into in a little bit. And then export that out of Scene to an XYZ file. And then we have a tool that we've developed internally that will essentially create an octree out of that data and compress it. We currently, we're not doing any sort of crazy compression algorithms on this stuff. It's largely just going from basically a basic scale and offset from the octree bounds. So you can take the data that's within a single octant and then store it in a byte format as opposed to a float. So you can reduce a fair amount of data there. And then anytime you're loading something, you just need the minimum corner of the octant and then the extent of it. And you can recalculate the actual floating point value of a point. But that cuts basically the point data from from 4 bytes per point, or 16 bytes per point down to 6. And then that essentially, in an example file we were doing the other day, when it came out of scene, it was like 53 gigabytes. The compression tool we made brought it down to 6. So much more reasonable, but at the same time, still not an ideal size file to then try to take and render. So, but at this point, then what we can do is take that file. It's then ready for visualization in our cave system in an Oculus Rift, and also in a tile display system that we use every so often. So one may ask why, and this came up a little bit during the panel, why not just try to make meshes of all this stuff? So this is just an example of the mesh on the left is what came out of Faro when we tried to do this. Now there may be other tools out there that I'm unaware of. I'd love to hear about them from people. If someone knows how you can get a perfectly textured mesh given just a point cloud that's very large in size, let's chat. But this is what happens in Faro scene is you essentially lose a fair amount of detail, obviously. And for this particular application, the VisHome application, we didn't want to discount the ability to potentially read writing on a wall, have enough detail to really discern what objects are, et cetera, et cetera. So this is why we're kind of going the approach of let's keep everything in a point cloud and work with that, even though it may sound a little crazy. But so touching on some prior work, had to give a call out to this. I don't think he's here, but many of you know Oliver Krylos, and he did a lot of his, one of his early pieces of work was bringing LiDAR data into a cave, and the cave they have at UC Davis. And I think they did a lot of that with geology applications in mind, a lot of so fitting of shapes to point clouds and pretty cool stuff like that. He ran this all through his Linux Rui toolkit. We were a Windows shop in Madison, so we kind of wanted to stay that route. We'd also developed a middleware at that point where we were building applications on top of that. So we sort of wanted to just take a different approach and try out some new stuff on our end, as opposed to trying to go work from where he started, although that may not have been a bad idea as well. So when it comes down to it, so problems with LiDAR data. So a lot of you are probably pretty familiar with this. So big one I touched upon, size of the data sets that come out. I think our largest data set was maybe in the 90 to 100 gigabyte range. Really, it all depends on how much time you have. If you have a long amount of time to scan a space, you could make a gigantic data set. Number of point primitives then that you're trying to render per frame potentially quickly causes problems. So to be honest, we tried the naive approach like day 5 of let's just render these using GL vertex 3F and throwing all the point vertices at OpenGL, and quickly we're approaching 5 to 10 frames per second only. The graph on the right is supposed to show is just some actual concrete data. We took a measurement of when you are rendering point clouds, so the horizontal axis, the number of points in the point cloud, or number of points per frame you're trying to draw, and then vertical is frames per second. So you can see quickly that as you approach, so going back to the 44 million point example of one scan, at trying to do that, this was a Quadro 5000 card, so a little dated at this point, but in my experience, it hasn't changed a huge amount. It has some, but you're already down to about 12 frames per second, and then with stereo, it's even lower, so you're down to 5 to 6 frames per second in this situation. So other issues that come up are uneven density of points that result from scans. So this is just inherent in how the LiDAR scanner works. It's all done on angular increments in terms of when it takes samples. So you can get, depending on where objects are in the scene, you can get points that are more or less dense in different areas. That causes issues then with trying to potentially render points of different sizes consistently, and just getting the overall scene to look good in general when you're rendering it. And then finally, something I mentioned before, right, is mirrors. So especially in interior spaces, something you didn't always think about, but what actually ends up happening is when you scan a mirror, the points then end up being reflected into that mirror in the resultant data set. So if you've got rooms adjacent to each other, you're just going to get a bunch of points that are in one room that were visible in the mirror show up in that room next to you. So you have to actually go in manually and cut out those mirrors as part of the post-processing process. Otherwise you have points in other rooms. And that's what this is trying to show down here. It's a little confusing, but the left side image is a mirror that we scanned. The right side is just showing that those points are actually showing up into the mirror. It's a side view of that bathroom mirror. So at one point with a tool, with a rendering tool, we actually had a mirror, a rendering pass built into it, so you could actually realistically see then a reflected version of the scene when you're walking around in front of a mirror, which is pretty cool. Problem is it cut down on frame rate quite a bit, so we've had it on and off at different times, and right now it's off, unfortunately, but we're probably going to try to bring it back sometime soon. So following that pipeline, getting to the point where we're ready to render stuff, tried this first approach, total bust. So what was our next step that we tried to do? So some of the basic kind of ideas that are helpful when you're trying to deal with really, really large 3D scenes. So create an octree data structure. Most people are familiar with an octree structure, so just basically a hierarchical spatial subdivision technique. What it allows you to do is basically only render content that's visible on screen, as opposed to having additional stuff being rendered that's outside of your potential viewpoint. That allows you to essentially, which is frustum culling. So then the other approach we decided to take with this from the get-go was an out-of-core approach. So what that means is essentially it basically nearly gets rid of this data size issue that exists. So the idea is similar to that basically whatever you're loading on screen in rendering is only what's in memory, give or take, at any one time. So that causes issues in the resultant rendered scene, but at the same time, it gets rid of this data memory problem that could really easily exist with some of this content. So given, say you have the ideal solution there, let's just say, even with that, you still are having this issue where you have a lot of potential point primitives you have to be rendering per frame. And what this causes is it causes your scene to quickly become geometry bound from a GPU bottleneck perspective. So, and this goes back a little bit to that graph I said. So you're still having to figure out a way to not render, basically render the optimal subset of points that exists for a 3D scene, for the full 3D point cloud. And then like I mentioned, the uneven sampling potentially also causes then more points to exist in different locations, which in turn causes more points needing to be rendered, which means there's a varying number of points needing to be rendered depending on where you are in a scene. And then that results in inconsistent frame rates, which is also not an ideal thing for interactive VR. So those problems still exist after this initial solution we took an approach and implemented as a poster at VR from a few years back. So to kind of try to take this to the next level, we had this idea, commonly known as image warping. We were calling it reprojection at the time. Someone quickly corrected us and pointed us to some papers that were talking about image warping. And the idea is essentially you're reusing content that's on the screen from one frame in the next frame. So the way you can do that is essentially take a bunch of represent the scene internally in terms of the points being in a world space and storing that in a buffer, in a floating point buffer. And then you basically take those points that exist from the last frame and then use your next frame's model view transformation to reproject those points to the next frame. So then you have a pretty decent starting point of points that existed before in your new frame. There's also problems with this. Points can alias themselves out. So if 2 points land on the same pixel screen location, one of those points is then gone. So that's not ideal, but that's the issue that you have to try to work, that we had to try to work through then to avoid or to just minimize essentially. The other approach we kind of added here was this approach that I've seen is pretty unique to a lot of the stuff out there, but this idea of because the data is so high resolution, let's see if we can we ideally render the detail at a point where it's 1 point represents 1 pixel. So some stuff that's out there will render splats so that, points will be bigger than other points. And then you'll get kind of these, while that minimizes holes in the data set, it causes kind of a weird effect. Stuff kind of is showing up on each other. There's ways you can blend it together, but that also is expensive, extra expensive rendering wise. So there's basically a level of detail type approach to let's just assume and try to render 1 point per pixel. So more details about some of this is in that poster paper as well. So unfortunately, I'm not gonna get into too many details of where we're currently at, but it more or less combines approaches from the past 2 approaches and adds additional improvements to kind of some of the depth artifacts and stuff that resulted from the reprojection concept. And I'll have it on demo here at the conference starting tomorrow, most likely, maybe today a little bit still, but and I got some different data sets we can take a look at if you're curious. So given this rendering engine that we kind of worked on and developed, we've used it for different research projects, added some interactive abilities to it, ability to paint colors. So you can go into a house, and this is part of the VisHome project, you go into a house and almost have like a giant highlighter that followed the 3D tracked wand, so people could make markings to indicate significance about certain spaces. We went through a whole kind of pipeline to make bounded objects, and some poor undergraduates at our lab were tasked with going into scene and manually creating bounding boxes around many point-based objects, and then we would export those. And it was most of them were good sports about it, but it then allowed us to essentially be able to have people choose objects in the scene, make choices, and this played it into the VisHome grant in terms of some of the research objectives that it was looking to do. We've done some other stuff where we've combined 3D imagery. So taking, as a result of the point cloud, you get a panoramic image as well. So played around with combining that with the LiDAR data. So if you go onto a spot where the original scanner is located, it swaps to the panoramic image, and they're basically co-located pretty well. That was more for a landscape architecture application. We've done different things too, where we could add audio, basic sort of audio narratives when you go on certain locations. And then this idea of physics, where you use the octants as a rudimentary kind of floor or area of a house, where you could just use that as your physics collider, essentially. So the actual octant data. Cool thing with that, and why we did it a lot, or why we aimed to do it, was we could make it so that stairs were really easy to use in a home. So you could just walk into a set of stairs and you just bump up them. So that was helpful for some of the work we were doing in the cave with VisHome. Particularly with people who weren't very comfortable with VR and just making it so that they kind of minimize the complexity of the user interface, essentially. So with this this VisHome project and this whole pipeline and rendering technique we developed, we have been fortunate enough to kind of take it to other additional applications. I'll touch upon some here. Touch upon those first 2 a little bit more detail, and the shipwreck stuff as well. We did a cave visualization of a data set that someone had scanned an actual cave in New Mexico as a part of a training process for I believe they're sending some researchers or astronauts to the moon to go inside of these craters. And there's these geological formations in New Mexico in these caves that are very similar to what these crater formations are like on the moon. So that was pretty cool. That was without color, but it was still a pretty cool sort of application. Yeah, let's get into some of these. The landscape architecture application was about, there's a professor very interested in studying walkability, and he was curious about using VR and LiDAR to create a data set of a outdoor space that happened to be around our building, and try to study how people can make use of that versus traditional techniques they use, which are typically like 2D maps, top-down views of spaces. So he's still working on some of that right now. So the crime scene investigation application, we have a project with the Department of Justice that's just winding down. We're looking to do a follow-up project, but this is all about actually more on sort of the cost and benefits of using this technology for crime scene investigators. So this all kind of started back in 2014. Patty got a call from the FBI and asked if there was anybody that was interested in helping them out, and heard that we had a LiDAR scanner. and there was a homicide 30 miles west of town in a small town. And Patty gave me a ring that morning and said, hey, do you want to go help the FBI out? And I said, okay, this might be a different Wednesday for me. So yeah, I'll give it a try. So I actually went out and did a full scan of a home where there was a homicide that had actually happened. We took that data set, sent it through a pipeline, processed it, had the Dane County Sheriff's Office come in, take a look at it in the cave. They use it to take a look around, see if they could spot any evidence that they hadn't already collected. They didn't actually see anything new in this case, but they're still fascinated by the technology and the potential impact it could have. And they had also heard there's various other crime scene investigation units who had started to adopt LiDAR scanning that they were aware of. So the point of the grant then was essentially to study, try to discover at what point does the initial investment that a law enforcement agency may have to do to purchase a LiDAR scanner, at what point does that potentially pay for itself, more or less. So we kind of went out and scanned a variety of mock, these are all, well, the upper left is a mock crime scene, the upper right is actually a real one. But we scanned a variety of mock crime scenes, collected data on the timing and number of points, and worked with a graduate research group that specializes in cost-benefit analysis. And we have a 3D online tool and a publication that's resulted, which there'll be a link at the end, that gives people a little tool so they could go on and actually see, okay, given the cost of this scanner, at what point, and giving all of these other factors, number of police officers that would need to be used at a scene, number of hours it would take, et cetera, et cetera. You can play with a whole bunch of different sliders, and it'll give you kind of a cost or a dollar amount in terms of when it would be saved over a year time, what would be saved or not saved over a year time span. So that link will be at the end. But the lower right corner image, just to note, is that the Dane County Sheriff's Office actually had a point gun, something called a PanoScan point gun scanner, which is more of a projected light, more of a Kinect-based technology for acquiring 3D scenes. So that became a pretty crucial part of the analysis in terms of having different comparisons of different kind of scanning technology, and then comparing the upfront costs between that and the LiDAR scanner. In the end, we just made it totally generic, so you could just set whatever values you wanted, just to make it so that since there's potentially going to be other scanning technology that's coming out. So another area we've really hit upon is area of cultural heritage. So upper left, we did probably the largest 3D scan of Frank Lloyd Wright's Taliesin that exists. Are you guys familiar with Frank Lloyd Wright at all? He's a pretty famous architect, Wisconsin native. His house still exists out in Spring Green, Wisconsin, which is about 45 miles west of Madison. I think it just became a UNESCO World Heritage Site. Really fascinating place architecturally. So we scanned that. We have a publication in the National Trust for Historic Preservation Forum Journal, just talking about combining LiDAR with VR and what potential benefits that could have for projects like this. The three images in that backwards L shape are just different sort of historically significant sites we've scanned in the Wisconsin area. Upper middle one, probably most interesting, is known as the Little Norway building. This was a church that existed at this cultural attraction site west of Madison called Little Norway. It was built back in 1893 for the Chicago World's Fair, and it was actually built in a way that it could be disassembled and reassembled, almost like Tinker Toys, kind of, in a pretty easy fashion. So what happened is this cultural heritage site was going to, the owners and operators of it decided they were going to sell it. It's going to shut down. It was actually in the family who ran the cultural heritage site owned the building, but they had a person randomly call them from Norway who realized that their ancestors had actually built that building back in 1893 before it was sent overseas to Chicago. So they actually commissioned and he sold it back to them. So now this building was deconstructed in Wisconsin, exists back in Norway. It was reassembled, but we have a 3D scan of it that is a part of the museum exhibit that is shown. It's about a halfway done picture of the exhibit, but it exists at a museum out in Mount Horeb, which is the town closest to where this building formerly existed. So people can still experience the building in 3D using VR, even though it doesn't exist locally anymore. So kind of a cool application of this combination of technologies. So another area we've been getting into recently, Shipwreck Reconstruction. So we have an undergraduate student, or sorry, he's just graduated. He's a research assistant with us, Bryce Sprecher, who has kind of become our Agisoft photo scan guru. So I don't know if any of you have maybe experimented with photogrammetry and Agisoft photo scan. You need to know how to turn the right knobs and move the right sliders into the right spots sometimes to get things to work well. He's gotten really good at that, fortunately. And he's actually gone out on some expeditions with the National Park Service, and they've gone up to the Isle Royale National Park, which is located in Lake Superior. This is the very northern tip of Wisconsin. And there's an island out there where a number of ships crashed and wrecked and back throughout the 1900s, and exists still down at the bottom of the lake. And he's worked with these marine imaging experts where they've gone and used some custom-built video cameras and technologies to capture videos and photographs of these shipwrecks. And then Bryce can use the photo scan to regenerate 3D models or point clouds of them. And then we've done different things where we can then visualize them in our cave using the same point cloud rendering engine that we built. And we're looking to do some work with Wisconsin Public Television. They actually happen to be doing a documentary right now on shipwrecks. So we're going to sort of do some supplemental content with them, hopefully related to this topic. So some next and future directions. So the rendering technology was patented through Wisconsin Alumni Research Foundation, which is like the technology transfer group at University of Wisconsin-Madison. If you're curious, you can look them up. They became famous because they patented warfarin, which is a drug, back in the 60s, and that patent ended up creating a pretty hefty sum of money for them. So they still exist in this area, and they seek to kind of promote technology, bringing it from the research end of things to market. And they're looking. We pitched the idea of, okay, now that we've spent all this time making this custom rendering engine, can we do all this in Unity now? Right. So we're about 60% of the way there probably in terms of having all this same stuff in Unity, and hopefully at some point working as like a plugin where you can drag and drop a point cloud into there, and it will render it for you in editor and in a game view. And it's, as many of you know, it's a challenge. I think we'll be able to get there, but it's going to take a little bit more time. Next, some other directions we've been exploring are just lower cost 3D scanning technology. So can we use, for example, the new Connect scanner to do some point cloud acquisition? Turns out you can sync them together as well, which is pretty cool. So the quality isn't going to be nearly as close as what a LiDAR scanner is, but the cost is going to be a lot less potentially. So there's potential benefits there. And then just other areas we've been thinking about and trying to get into are, what if you took point cloud captures of the same scene over time? Could you somehow show changes over time of a point cloud? And then this whole issue of segmenting objects. So these poor undergraduates don't have to segment any more objects with their other algorithms out there. I know there are some algorithms out there, but we just haven't really looked into trying to integrate them into some of this work. And finally, sort of the problem of even if you have an object segmented, if you were to move it, you have blank space behind it. So what do you do in that case? So some quick conclusions. Point cloud rendering is hard. We've developed a solution that gets us some acceptable frame rates, 40 to 80. That was what I was going back and forth between when trying to run this on and get this ready for the S yesterday. And then what it comes down to is this ends up being a loading speed versus frame rate trade-off. So the more points you're trying to render any frame, the slower you're still going to be. And then there's also a trade-off that can happen with the actual reading speed that exists, bringing that data in that out-of-core fashion. So just finish up with some questions of the group. Interested in chatting with you folks about LiDAR. And thanks again for having me here. One quick note is that vishome.org, we actually have those 20 homes online for download. And there's 2 different versions of them. There's a high resolution, super dense version of them. Then there's actually one we sub-sampled down to 1 centimeter difference between points in a house. So just to try to make them a little bit more accessible. Yeah.
Cool. I think we have time for maybe a question or two. Cutting a little bit to a break, if that's all right. Anybody has any questions? All right.
Yep.
Just a moment.
Very interesting talk. Very interesting talk. I enjoyed it. My comment is, don't you see any merits of converting a 3D point cloud into a mesh, kind of mesh rendering? Because I saw that you did a comparison of mesh versus a 3D point cloud by collecting the data itself. But is there any merit? For example, in engineering applications, I saw that they scan a big clean room, then we have to report that complete mesh, automatic mesh.
Yeah, I mean, I think it comes down to your application. There's some things where, like I briefly quickly mentioned at the end there, where in the point cloud format, you saw this issue of if you were to get to the point where you could move point cloud objects, let's just say, let's say you've kept an object as a point format, but you've segmented it, so you have a distinguishing kind of transformation for that group of points. You move it out of the way. If you haven't scanned behind it, you're gonna have a hole in the scene. So if you're running an application where you need to move objects around within that scene, there is benefit of trying to go to a mesh and fully enclose that mesh from the points. Now it gets difficult, right? Because if you haven't scanned behind an object, then that data is missing. So you need to just close it off. Give it. I'm thinking of like a can or something, a soda can. If you haven't scanned behind it, then you might be able to do something smart where you just flip the front part of the cylinder to the back. But then if you got a more complex object than just a cylinder, for example, then what are you going to do? I guess you just put a flat back on it, stuff like that. But that is the one downfall of working with this data. A lot of these applications I discussed, it's been more the scene as static is really all we need and what is needed for the particular research question or project. But that's where I think some additional research focusing on this stuff could potentially bring some benefit. Is the idea of in-painting, which is it's a common 2D algorithm where you try to fill in images with information that makes it look seamless. If you were to move, if you were to change it some fashion, I think there's people that have worked on 3D versions of that for point clouds, but it's been a little bit few and far between. Although don't quote me on that. It might, I think there's continued work in that area. So.
Did you say your lab developed the geo-registering of panoramic image with the 3D point cloud?
No, we didn't develop that. No, that. Well, yes. Sorry, yes. Yeah, we made a version that lets you basically export all of from Faro scene, that intermediate application. You can export the original scan locations, and then what we did for a landscape architecture application is that we just indicated those locations by a little disk on the ground in the point cloud scene, and then when you go onto that, it would flip on the panoramic image.
Like you created markers like on points.
Yep.
Ross, great presentation, thank you. Just as you were talking, you might want to poke around Autodesk and see what they've been doing, because although they haven't been working with LiDAR specifically, they've definitely been working with some of the issues of photogrammetry. And cool. Trying to take that into, trying to justify some of those point cloud, some of those images basically a little bit faster and clean up the images. They're really now, in fact, they offer kind of post-processing service basically, but since it's Autodesk, just poke. Don't give away what you're doing. Just, they're really, really hard to get. They don't share much.
Right.
So,
Yeah.
Okay.
Yep.
So but it might be worth it. There might be something out there that is useful.
Thank you. That's good to know.
All right. Very good. Thank you, Russ. I think we'll wrap up with that.